For this video, let's run through the test review for Chapter 16. And I just want to make a little comment that the notes you see here in this box is specifically for, semester fall 2021 in terms of what's on Test 2, what's on Test 3. If you're watching this at some other semester, please refer to your notes, course announcements, etc. to know which problems apply to which test. Okay. One other thing I want to mention is just a reminder that there are timestamps in the description of this video so you can jump around to the particular problem that you're curious about. Okay, so for this first problem, this is a real kind of standard ICE table calculation of pH for a weak acid. And the first step here is the recognition that something like this is happening. Okay, we have our weak acid and it is dissociating in solution. Okay, so there's a conjugate base, and we know we know three facts and then some data. We know that we are starting out initial concentrations. We know that the initial concentration for the weak acid is 0.1 molar. That's given in the problem. Nothing else is stated in the problem, so we can assume that the concentrations initially of the proton and the conjugate base are 0. Right? We're pretending like initially it's no dissociation has occurred. Now, the dissociation is really described by the change line. And for this particular problem, and just like many of them, we are going to use X as a value to represent how much change is occurring during the reaction, during the going from initial to the equilibrium condition. Now, I placed X on the product side here because I know that since I'm starting out at 0, I know something has to change there. I know something is going to be added to the final solution that we're going to come up with in just a second. So on the product side here, this is a positive value of X. It's going to increase here. Now, X is going to decrease on the other side by some corresponding value. Now, in this particular example, and in many of the hydrolysis reactions you see in Chapter 16, that's what it looks like. It's going to be just 1X all the way across. But I just want to point out that the reason why it's 1X all the way across is because these hydrolysis reactions, even for di or triprotic acid, are done in stages of the loss of a single proton, and the result is a 1:1:1 ratio for the X's there. Right? If there were, for other examples, if there were coefficients such as 2 there, then it would be a 2X change on the C line. All right, so I have my I and C established, and basically you're just combining I and C together. All right, we can say 0.1 minus X gives us this new equilibrium line. Similar kind of logic here, 0 plus X, which is X, gives us the equilibrium line for both of those. And now, if we're at equilibrium, then really we're ready to then approach the Ka value there in the equation of it's this, the ratio between the products and reactants for any kind of equilibrium constant. Now this is in molarity, so it is in concentration. So instead of substituting in some kind of quantitative value, really you're just using what's on this equilibrium line to represent what is unknown, really, in some ways what's known, for the concentrations for the individual products and reactants there. Now, this expression is then equal to this value, this Ka value. And like we've seen in class before, if we evaluate this expression at this point and solve for X, it is a quadratic formula. and we don't want to do that. So your typical approach here, and I'll just point out a couple little things here. Okay, one thing to note is that the Ka value is really small. Now that's not the main criteria that we use to determine whether this approximation could be used, but it's certainly suggesting that it's going to be okay in this particular case. It's actually the percent ionization that tells us whether we can use the approximation. For right now, we're just going to go with it, and I'll address that approximation, whether it's valid or not, in sort of a later moment in the discussion here. Okay, so if I go through here and I simplify the expression with the approximation, I look like that. And we can evaluate this exactly using a calculator. So basically what I'm saying is that this value of X here is so small compared to the initial concentration that we can ignore X. And we'll see that is the case. The ionization, percent ionization of this acid is really small, and we'll quantitate that at the end here. Now, what I want to do is I want to solve for X, and X is now going to be equal to, and I'm going to carry out more digits than I really could use if this was my last step in the calculation, which it's not. But X is equal to 10 to the minus 5 there. And now we are going to reinsert the molarity unit, in recognition that this is dealing with, well, it's the constant. We could insert X into the equilibrium line here and determine the equilibrium concentration for all of those components. Now, since we're just determining the pH, we only need to know the proton concentration. So I'm going to say that this is equal to now the proton concentration. And then the final step is the calculation of the pH, and it's going to look something like this. Right, all pH equations have this form, and I'm simply going to plug my value in here. And when I evaluate this, I come up with a pH of 4.26, which is kind of what I expected. If I'm paying attention here, right, the exponent that we see for the value of the concentration is going to be close to the, I'm looking at just the 5 sitting there. It's close to the pH value here. So you can sort of always eyeball whether you're sort of on the right track here. Something else to note is that I am at an acidic pH, and that makes sense because I'm doing an acid. That can often give you a heads up whether you're approaching this correctly. For example, if it's a weak base and you're getting an acidic proton, probably what's happened is that you've forgotten to go through the pH step for those weak bases. So just a little heads up for you there. Now, in terms of calculation for this problem, it's answered. Okay, the pH is going to be 4.26. But what I want to do, just for a real quick moment, is I'm going to do the percent ionization here. Now, percent ionization, the formula is given in the equation sheet, and we've seen it in class before, so I'm not going to rewrite it here. And actually, I'm going to shorten my concentration of the acid just a little bit. But it takes on this form here, and it's a percent, so it's going to be times 100. Right, so this value, right, that value is just X, the amount that has dissociated, the amount that has formed, over the initial concentration, which, was given in the problem there. So it's like how much you have versus how much you started with, times 100. It's a percent calculation. And when you do that, what you find is that the percent ionization for this one is really small. It's not even 0.1%. Right, so the percent, we could say the percent ionization is less than 5%, so the assumption is correct. Right, if it's over 5%, that we need to use the quadratic formula. Let's talk about the quadratic formula just real briefly here. So like I said, it's this portion that if you evaluate it as written, it's going to give you a quadratic formula. And if the percent ionization, again, is greater than 5, you got to use the quadratic formula. You got to solve this X exactly. Now, there are 2 other methods you can use, and there are videos online to show you how to do that. on our Moodle courses. Okay, one is using a graphing calculator. You can plot these two components and where they intersect, give you the roots of the quadratic formula. And in the other case, there are just formulas where you can plug in this expression and it'll just solve it. It'll just solve for x, which is, right, it's the root. Now, since the percentization is so small, whether you use the approximation or the exact solution, it's still going to be close to that 10 to the minus 5 value. And the pH is going to be close to that 4.26. And then the last thing, just briefly, let's talk about the sig figs just for a moment. So in terms of data, I would probably consider the concentration the most important data point here. As it turns out, both values that are given in the problem agree with each other, meaning that there are 2 sig figs in that answer. And so if we go through this process, that would pretty much establish 2 sig figs if we were to stop at the concentration stage. We don't want to, right? We want to then take the negative log of that. And remember how that works. The approximation that we use is that the number of sig figs in our answer dictates the number of decimal places that we carry the pH value to. And that's the case for any type of some value. If you're taking the log of some value, you always apply that rule. Okay, so that one's done. Now in this next one, this is just a little bit of practice going through, right? There's all these equations that relate pKa, pKb, Ka, and Kb. And you need to know how to use all of those formulas. And we'll use all but one of them, I think, in this particular example. And what we have to remember here, and let me just sort of write out the hydrolysis equation just for a second and just make sure that we're all on the same page. All right, so we have the acid here. We have the conjugate base there. And these equations that we're talking about relate either the Ka or the pKa, whichever form you're talking about. So it relates the Ka information about the weak acid to the pKb or the Kb information for its conjugate base specifically. And the equations, like the first one we're going to use is this one here. So the pKa and the pKb of any acid conjugate base pair is going to equal 14. And so if Ka is given here, then if I just solve for the pKb, it's 14 minus pKa. These equations in the grand scheme of things are not too bad. And so if I evaluate that, that comes in at 3.4 as the pKb value for this, actually the pKb value for the conjugate base. All right, this relationship is true, again, for any pair of acid conjugate base molecules here. Now, when we want to go from the pKb or the small p of anything, pH, pOH, pKa, what we do is you can use the anti-log, so it's a shift function of the log button. But typically what I do is take the, in this case, the value of the pKb and raise 10 to the negative of that. Okay, so what it looks like here is 10 minus 3.4, and if I evaluate that number, I get the 3.98 times 10 to the minus 4 for the Kb for that conjugate base. Now, the last thing I want to address for this example is just a follow through with the sig figs. So I use sig figs properly, like this is a subtraction operation, so I need to carry the same number of digits as my original data. Right, we assume that this 14 is like an exact value. We can ignore the sig figs there. Basically, it's 14.0000, however many zeros you can imagine, whatever. Okay, so 1 decimal place is fine there. Now I'm going the opposite direction than what I did just a minute ago. And I want to go from the lowercase p to the, the full-blown number here. So if I'm talking about 1 decimal place here, that means that I'm talking about 1 significant figure in my KB value. So really, the correct value here is 4 times 10 to the minus 4. Okay. So just wanted to address the sig fig with you one more time, dealing with the log function. This problem is very similar to what we just saw, really. We're still going to go through the rigmarole of all of those different formulas, but now dedicated to the pH. Like for example, what we find is that for any solution out there, if we add the pH and the pOH together, we get 14. And notice it looks very similar to that expression up there. They are related to some extent, and you can look at the book for that. On the test, I'm not going to ask you to give me an essay question about that topic, so don't worry about the details. It's really the mechanics of using this this information, these equations. And the reason why I start off with this equation here is because that's really the first thing that I want to approach here. I'm going to go from the concentration of the hydroxide to the pOH, and then to the pH, and then to the hydronium concentration. So those are the steps I'm going to take here. And the sig figs are going to be fun too, and you'll see that in just a minute or two. All right, so if I want to calculate the pOH of a problem, right? If I see, just like I've said before, if I see the lowercase p of something, right, that means that I'm taking the negative log of that something, in this case the hydroxide concentration. So when we do that, that value is going to be 3.8099, and I am writing out the proper number of sig figs here. So I have 4 sig figs in my quantity here, and then when I take the log, that means I need 4 decimal places in my answer. Okay, so that is correctly done. And now the next step, I want to calculate the, I want to take this and I'm going to rearrange it to calculate the pH. So that's going to be 14 minus the pOH. And so it's 14 minus the 3.8099. And then that is equal to 10.1901 for the pH. So it is a basic solution, so we can go ahead and answer that part. And then finally, let's now go from pH to the hydronium concentration. And it's going to be similar to what we just saw back up here. And what I mean by that is that the hydronium concentration, right, is going to be now equal to 10 raised to the minus pH, 10 raised to the minus 10.1901. And then if we use our calculator for this, with the proper number sig figs, we get 10 to the minus 11 molar for the hydronium concentration, which is pretty low. Right, for a basic solution, anytime we're talking about a basic solution, the hydroxide concentration is going to be greater than the hydronium concentration. And we can see that just by eyeballing the coefficients there. That 10 to the minus 4 is greater than the 10 to the minus 3. While I'm thinking about it, I haven't used this type of equation yet, but let me just comment that there's another way to approach this, and if you did it this way, it will work just as well as what I did here. If you multiply the concentrations of the hydroxide and the hydronium, you would get 10 to the minus 14. So like in this example, you could have determined the hydronium ion concentration first by plugging the hydroxide concentration into this formula, and it would give you a value pretty close to that. There's always a little bit of difference, not always, I guess, but it's very common to see a little bit of difference in the lower end of the decimal places there. But the order of magnitude is not going to change. This exponent is not going to change. Either way is a proper way to approach this problem. And then just to finish my thought here, if I had calculated hydroxide first, then I would have gone through probably this sequence in terms of the order of calculation. Right? Calculate pH first and then the pOH. Either way, either path works for these types of calculations. So in this test review, there's actually two different problems dealing with this kind of topic, where, am I getting a acidic or basic solution when, some said salt dissolves in water? And what you have to recognize, and I'll just sort of quickly break this one down, because really, this one is a little bit different than B and C here. So these two ions get produced in solution, and yes, you could do the molar coefficient there. That's fine. It's really just you're looking at the individual ions and you're asking, well, are they acidic or basic at this point? Well, one thing to note is that nitric acid, that's the conjugate base of a strong acid. So that means it's not basic. All of the conjugate bases of strong acids are really stable in solution. They have no tendency to pull off protons from water, so it's not going to affect the pH. And then we learned that the magnesium cation can undergo a hydrolysis reaction and become an acidic solution. Problem number 5, I'll show you an equation of those metal cations and how they generate hydronium ions in solution. Now, most metal cations on the periodic table will cause an acidic solution to form, except for like the first family. So potassium and sodium do not cause acidic solutions to form. So like in B and C, what we're talking about here are really the anions. So let's look at this ascorbate one first. So we have this formula. And what we have to recognize, well, one thing, it has a -1 charge, right? It is a salt. Potassium had a +1 charge, so it's equal and opposite charge for the cation and the anion. And then the other thing we have to recognize is that this thing has a little bit of a split personality. The proton in front would suggest that it's an acid, and it can act like that in some cases. And then the fact that it's an anion says that it can also act as a base. And so what happens, and sometimes the phrase is this is an acid salt. I don't know if the term is used terribly often, but you might see it, so I just want to share that with you. So what happens is that, you get two different reactions occurring in water, two different hydrolysis reactions. I'm going to add water to both of these reactions. And in the first one, I'm going to make it an acid. And in the second one, I'll make it a base, and you'll see that in just a moment. And you get hydronium here. And that's going to be governed by a particular Ka or pKa value. Now, the tables that we use are pKa values, so let's use that. So, and I'll come back to the significance of that number later, but basically, if there's a large pKa, this is not a very strong reaction, so keep that in mind. Now, there's another reaction that's occurring in solution, and it's starting off with the same molecule, right? This molecule can act as an acid or a base, and this one I'm going to write out as a base here. Now, when we do the hydrolysis reactions for a base, we have to add water because water is actually acting as the acid, right? That proton is going to go in that direction. And so what we do is we actually reform the ascorbic acid over here. And hydroxide ion. Now, what we have to figure out now is the pKb for this molecule here. So if we want the pKb of this molecule that expresses its tendency to act as a base, we need to know, or we need to look up or be given the pKa for its conjugate acid. This equation that we're about to use and that we've used before, that equation is only true for acid conjugate base pairs, or in this case, you could say base and conjugate acid pair. So if I look up the pKa for ascorbic acid, I get 4.10. And then once I have that value, this calculation becomes much simpler. The hard part is recognizing that this relationship requires that you go out and find a new pKa, okay, the pKa of that conjugate acid from the base there. But then the math is pretty straightforward. We've seen this math before. This gives a pKb of 9.90. And what you have to remember is that when you talk about, when something is that, if you've taken the negative log of some expression for this chapter, what you have to recognize here is that the lower you go, the more whatever, the more basic or acidic, if you're talking about a pH scale, or if you're the more if you're talking about pKa, pKb, you're really talking about more products being formed. So the fact that this pKb is smaller than the pKa, that means that since the second equation is the one that's going to go in the forward direction more so than the first equation. So the net result is that you're going to get more hydroxide at the end, so this is a more basic solution. Again, both equilibria are occurring, but this one is such a large pKa that it really doesn't go to the forward direction to any extent, especially compared to the second one, which has that smaller pKb. Again, just like a pH scale, if you're talking about something that's very acidic, you're talking about a small pH, pH of 0, pH of 1, pH 2. Now in that second one there, this one says hydrogen carbonate. Now the first thing I'm going to do is actually going to write out the equations first, meaning the hydrolysis reactions. So if this one is acting as an acid in this first one, and that's typically what I do, because usually it's the pKa that you're looking up anyway. So that there's one equilibrium reaction that's occurring in solution. And then the other equilibrium reaction that's occurring in solution is when this acts as a base. So we've got to add water for this one. Right, so the base accepts a proton, so we get the carbonic acid, and then we get the hydroxide ion. And again, if you look up the pKa for this one, actually, I'm sorry, I'm going to, just to change it up a little bit, I'm going to use the Ka for this one, just so I cover all my bases in terms of the topics that you need to be familiar with. Now the Ka for this acid comes in at 5.6 times 10 to the minus 11, and that would result in a pKa of around 10 or so. Okay, so again, it's not a reaction that's going to go in the forward direction very much. Now whether or not it's going to be the dominant reaction, we don't know yet, because first off, we have to figure out its tendency to go through a Kb reaction, or what the value of the Kb value is how I should say that. And to do that, I need to know the Ka of its conjugate acid, in this case, this guy. And I'm going to use, it's an analogous equation to what we saw there. Right? If I multiply Ka and Kb together, it's always going to give me that 10 to the minus 14. So if I want to evaluate the Kb, then it's 10 to the minus 14 minus, or divided by the Ka. And in this one, just to be clear, the Ka is this guy from the conjugate acid. And now this value is 2.3 times 10 to the minus 8. Now in this example now, as the Ka or Kb, just any equilibrium constant, as it goes to a larger number, then the products are more favored. Now in this example, what I need to evaluate is that value versus that value. And what I see, if I just look at the exponent, that's all I have to look at here, I see that the Kb is greater than the Ka. Therefore, this solution is basic. So the larger the Kb, or the larger an equilibrium constant, the greater tendency that it has to go in the forward direction there. And this is a relative thing, okay? I'm not saying that this is a strong base or anything like that. I don't know what the pH is. All I'm saying is that compared to these two equations, it's this one that's going to win out. And so the net effect is going to have a greater hydroxide concentration, and therefore it is a basic solution. And before I leave this problem, again, I just want to emphasize that this equation, again, is true for that, or maybe I should say that acid and its base. So remember, when you apply this equation, keep it within the acid base that's in a particular equilibrium reaction. Now, these are just some examples of some practice problems dealing with hydrolysis reactions. And I've set this up to where, well, since there's no protons in front there, it's going to act as a base. Here's an example of one of those nitrogens carrying a positive charge with a hydrogen, so it's going to act as a weak acid. And then this is our hydrated metal complex, and this is going to act as an acid as well. So notice I'm not telling you whether to draw the hydrolysis reaction for an acid and base. You need to be able to recognize, am I looking at an acid or base, before I can then move on to the next step. Okay, so in this first one, right, if the phosphate is the base, that means water is the acid. And if I do the proton transfer, I get hydrogen phosphate. Notice how the charge increases by 1, right, because the H plus is going over to the phosphate. And I guess just to be, technical, there's AQ tags there. L tag for water, it's a pure substance. And then, since it's the base, I'm going to get hydroxide forming. And now what we say is that, okay, whatever was the base then forms the conjugate acid, and then whatever was the acid forms the conjugate base. In this next example, actually in the next two examples, water is going to be playing the role as the base. So it's going to be accepting the proton. Now here, the proton that's accepted is actually one of those protons. It gets transferred over to the base there. Right? And what is happening? What is transferred? It's an H and a positive charge. So the acid that now forms our conjugate base over here on the product side, it loses one hydrogen, one proton, and it also loses that positive charge there. And again, I just said this is a conjugate base. And then once water accepts that proton, then we're forming hydronium in solution there. And again, I should have AQ and liquid over here, and that would mean AQ and AQ for those phases. Here, AQ for the hydrated metal complex, and then liquid for the water, of course. Now just since it's been a while since we've talked about this, let me just address that structure real quick over here. So remember, the aluminum, and I'll just show one example. There are empty orbitals on these metal cations, and they are spaces where lone electron pairs can then bind to. And so basically you form what's called a coordinated covalent bond there, and this can happen, 6 water molecules can clump around this metal cation, and that's fairly typical for metals in the periodic table. You don't need to predict how many are going to form. That would be given to you. Now, since we're talking about this, This would be, this is donating the electron, so it's considered a Lewis base. Right, that's that third acid-base model that we learned. Whatever accepts electrons, this is our Lewis acid. Now, this Lewis acid-base reaction is occurring, instantly in water, if you will. And then once that forms, then this hydrolysis reaction can occur. And we're just looking at just basic hydrolysis reaction. We're not going to get into the chemistry, anything beyond that. And they do change the pH. This aluminum solution at a decent concentration, I think, can do a pH of 2 or 3. I mean, it's a substantial pH change. So since it's acidic solution, that means that a proton has to be coming from this guy somewhere. And if I look on the structure, I mean, there's only one source of the proton. It's that water molecule. So what happens here is when that one proton is donated, one water molecule gets converted over to hydroxide. So of the 6, 1 is lost. So now I have 5 water molecules. And I said that it gets converted into hydroxide ion. And as it turns out, and I don't need a charge there, and as it turns out, that hydroxide molecule stays bound to the aluminum. So you get a new metal complex, metal ligand complex. So you can count both of these, or all 5 water molecules in the hydroxide as ligands, or you could even say Lewis bases that stay bound to the aluminum. Now, in terms of charge, let's just take a moment here. The aluminum has a +3. We know hydroxide has a -1. So the net overall charge here is actually going to be +2. Once a proton is transferred over, then we get our hydronium. And then in terms of conjugate base, conjugate acid labels, it's just like we've done before. Right? Whatever was the acid, once it gives up a proton, we say it's the conjugate base. And then hydronium is going to be the conjugate acid, which I actually forgot to write here. That's the conjugate acid. And just to finish this off, both of these are going to be aqueous solutions. Now, this type of reaction is occurring with pretty much every metal cation, except for the first family and then a few in the second family don't do this. Like the example that we did just a minute ago, magnesium. I said it forms an acidic solution. I didn't write out the equation, but it's undergoing the same kind of process here, where it's getting rid of a proton there from the water that's bound to it through this kind of Lewis acid base model that we're talking about. Now, in the last one here, okay, there's no acid salt, thank goodness, but it's the same kind of scenario where you're basically comparing one solution to the next. So imagine that, you got one solution of that's sodium hypoborite. You don't need to know the name. And this is sodium borate. 2 separate solutions. And we want to know which one is more or less acidic or basic, okay? And, one thing we have to recognize is that each one of those, if we think about if this thing dissociates in solution, we get these molecules forming. And we have to remember that the sodiums do not affect the pH. So it's really just the conjugate or the bases here that we need to worry about. And if you look at, what's the difference between these bases, it's really just the number of oxygen atoms that are bound to that central atom. The charge stays the same. Bromine is still the central atom. And those are the comparisons we'll make. Okay, it's not like we're gonna compare bromate to chlorate necessarily for this. Right? It's this kind of variation. Now, the quick take-home message. Okay. The fewer oxygen atoms, the more basic the solution is going to be. And so we could say, if one is more basic, then this one would be more acidic. I'm not saying it's pH of 4 or anything. I mean, it's probably it may just be a pH of 7, honestly. No, actually, it wouldn't. The bromate would act as a base to some extent. And maybe I should say less basic. That's probably a better way to say that. It's a less basic solution than that first one. Now, so that's sort of the take-home message, right? Just this. So the fewer oxygens on the polyatomic ion, then the more basic it's going to be. So just briefly, why does a greater number of oxygens produce a less basic solution? Well, essentially, and again, long story short, these are resonance stabilized, more so than the other guy. Okay? The greater number of oxygen atoms, you can draw more resonance structures. The argument is the more resonance structures stabilizes the molecule more. It kind of spreads out that negative charge better. And so if BrO3 is more stable because of this resonance phenomenon that we know about, then it's less basic, right? Because we know it's a base. I mean, we know it's a base. It's carrying a negative charge. It is an anion that is not a conjugate base of a strong acid. Therefore, it is basic. I know that phrase, you got to think about it, but it's true. It's something that we rely upon all the time for these types of reactions or these types of questions. Like, for example, in this next one, chloride. Right? So chloride is a common ion to those two salts. So that suggests that chloride isn't the thing that's going to dictate whether it's ultimately acidic or basic or more acidic or less acidic, however you want to phrase it. Why is chloride off the table here? Well, because it is a conjugate base of HCl. That's a strong acid. Therefore, it's not basic. It's not reactive in an acid-base sense. So that leaves the two cations there. And we have two separate cations. Right? The 2 here matches up with the 2 on the charge. The 3 chlorides there matches up to the +3 charge on the ferric ion. Right? Nature likes to balance everything. The -3 or the -1 3 times, that's an overall -3 charge, and that's needed to balance out the +3 there. So that's how we know what the charges are for those cations, right? Because the vast majority of the transition metals and post-transition metals on the periodic table are variant, meaning they can take on 2 or more different charges in solution just depending on their chemical makeup. Okay, long story short here is that this one is going to be more acidic. And the reason why that is because it has a larger positive charge. When you have that larger positive charge here, then when it forms, and in solution, I'm going by my memory, but this thing probably forms with 6 water molecules around it. These hydrated metal complexes here. And there's a coordinated covalent bond that forms between the ligand, right? The ligand here. Or we could say the Lewis base and the Lewis acid. And since this has a greater positive charge, it actually pulls in electron density to a greater extent into its core, if you will. And what happens is it weakens this bond, and so that proton is more likely to be kicked off. And if that proton is more likely to kick off, that's why we see that this one is more acidic. Again, both are acidic, it's just that the higher the charge, the greater the hydrolysis reaction, therefore the more acidic that is going to be. Now, in our last example, okay, what's different? Well, it's actually the nitrite versus the nitrate. Now, it's true that zinc is going to cause the solution, if it's just zinc by itself, sure, zinc is going to cause it to be slightly acidic, but since the zinc plus 2 cation is common to both of these salts, then its effect is negated, if you will. Okay, it's the nitrite versus the nitrate that we really want to focus on. Let's do that. Now, since they're both anions, they could both possibly be basic. Now, this one is not basic for the same reason as I said up here. And actually a previous problem number, it's, when I say it? I said it here. Same thing. Nitric acid, or nitrate, is the conjugate base of nitric acid. It is a strong acid. And I'll just use this opportunity to remind you of a few things. Right, it's a strong acid, so it disassociates essentially to 100%. So its tendency to go back in the opposite direction is essentially 0. That means this thing is non-reactive in an acid-base sense. Okay, and it can do other things, fine, but in an acid-base sense, it's non-reactive. Now, this one, however, is not. This one is going to be more basic because it is, well, it's the conjugate base of nitrous acid. Oops. And it is a weak acid. So whatever, if you have a conjugate base of a weak acid, then this is a weak base, just like I said. So the answer here would be like, this solution would be more basic or less acidic. I mean, you're really describing the same thing there. So where does it fall on the pH scale versus that other salt? Okay, I hope this was helpful. And remember, there are timestamps down in the description of this video that allow you to jump around and view individual problems so you don't have to watch the whole thing. Okay, thanks.